Welcome, everybody. My name is Keshav Patel. I am a third-year PhD candidate at the University of Utah studying applied math. And welcome to our Essentials for Math Modeling workshop series. This is week one, our overview workshop. To get started, I'm just going to talk a little bit about the goals for this workshop in general, what we'll be expecting to talk about. I'm going to be introducing our amazing volunteer and leadership team that's going to be working with us during our workshop today and during the rest of these 7 weeks. And then I'm going to actually get into the meat of today. All right. So for overall goals, this workshop series is going to be geared towards high school students and obviously educators and anybody else who is maybe interested in listening to what we have to say is welcome to be here. But we're really going to be gearing this towards the high school student who is potentially going to be competing in the M3 challenge. So during the course of these 7 weeks, some of the things we're going to be doing is applying general modeling principles to real world problems. What that means is we're going to take a real world problem and ask, how do we turn it into a mathematical problem? Some of the things that we're going to be doing today will be defining mathematical problem statements, making assumptions, and defining variables, things that we can actually quantify. Afterwards, in the next couple sessions, we'll be talking about things like actually building models, analyzing and assessing models so that we know that whatever model we build is actually relevant for the problem that we're going to be tackling. All right. Another thing we're going to be using is programming skills and data analysis. So we're going to be using Excel and the MATLAB programming language to analyze data, run simulations, build figures for your reports. Other things we'll be doing are applying basic statistical tools like linear regression and potentially some sensitivity analysis, all with the goal of making sure that your model is a good model. The fourth goal, and perhaps one of the most important goals, is to be able to read, analyze, and identify strong aspects of model reports. So we're going to be taking a deep dive into several previous M3 challenge problems as case studies, and we'll be looking at good solutions and potentially some non-winning solutions. And students should be able to compare and contrast and hopefully understand what should go into their own reports to be successful in this competition. All these goals aside, it is not required that you do participate in the M3 challenge in order to be a part of these workshop series, but that certainly will be something that we'll be focusing in on during these workshops. All right, some other just kind of bookkeeping, kind of housekeeping announcements. If you are interested in competing for the competition, some things that you might need to be aware of is that you should start building a team sooner rather than later. These teams should consist of 3 to 5 students within your same institution. You're also going to need some kind of advisor, somebody who at the bare minimum will be able to register you and download your problem for you and submit your report at the end of your challenge window. Some really important dates that everybody should be aware of if you're interested in competing. The registration window closes on February 18th at 4 p.m. Eastern time. And the competition itself is a 14-hour window between the dates of February 25 and 28. Right, so these are things that you should take into account taking a look at the chat. These are things that you should take into account when you are thinking about potentially competing. Some other housekeeping things. We are going to be using this Zoom webinar for our workshop series for the duration of this time. We ask that you ask questions through the chat. It seems like the Q&A is working, but for at least today, we ask that you use the chat for any questions, and some of our volunteers will be able to answer questions, or I will hopefully get to them at some point during our talk. One really important component that we ask you all to do so that we can make sure that this workshop series is successful is to participate. Particularly during our second hour of our workshop series, we're going to be asking for participation from our audience in order to really drive discussion. So if you all could be willing to participate, that would be really great. And of course, as always, we should be respectful of other people's ideas and contributions. An idea that I will kind of get to repeatedly during today is that different ideas from different people are going to be really helpful in order to be successful in mathematical modeling. All right. The next thing I'm going to do is introduce our workshop team. So myself, Keshav Patel, and Dr. Wesley Hamilton are the co-leads. Wesley is a PhD in mathematics and also a postdoc at our university. Myself, again, I'm a third-year PhD candidate, and I previously have competed in competitions like the M3 Challenge back when I was in high school. We also have several really incredible volunteers who are going to be taking over our workshop series in the future. Owen Kopp is going to be taking over the second half of this hour. He's also competed in previous M3 challenges and is an undergraduate here at the University of Utah. Julie Sherman is a third-year PhD student. Nathan Willis is a sixth-year PhD student, and Dr. Zhao Shen is a postdoc here. So again, you'll be able to get to know all of us fairly well by the time this is all over. A quick note about programming. This is finally getting to the question that's in the chat. We're going to be using MATLAB in order to do all of our programming for the duration of this workshop. Any programming language is acceptable for the competition itself. However, for this workshop, we're going to be using exclusively MATLAB. Everybody should have a temporary MATLAB license available to you. If you've registered for this workshop or for the competition, you should check your email for instructions, your confirmation email on how to register for a MATLAB license. And then you'll be able to either download the MATLAB IDE software or use the online version called MATLAB Online. All code is going to be posted here where this hyperlink is, but you can also take a look at the chat message where it says link to code. This is a MATLAB file exchange website that is under my own profile. I'll be posting code here as we go along. Next week's introduction to MATLAB script has already been posted there. So if you want to take a look at what we have in store next week, you are more than welcome to do that. Also, I should mention that these slides are all hosted on Google Slides, and the link to that is given. I don't believe any of these slides are currently on that Google Drive, but they will be as soon as this workshop is over. Just road mapping for the next couple weeks. What we're going to be doing today is talking about the mathematical modeling process from kind of 1,000 feet up. Then we're going to be taking a couple weeks and looking at programming. We're going to be starting from basic programming without assuming that anybody has any prior programming skills. Then we'll talk about some data analysis using MATLAB and Excel. Weeks 4 through 6 are actually going to get into model building. So we'll be talking about difference and differential equations, probabilistic models like Markov models, and then things like linear regression and other statistical ideas. Week number 7, so February 22nd will be after the registration deadline for the M3 challenge. So by this time, everybody will know whether or not they're going to be competing. And this session will be on writing practices for your report and talking about maybe some Q&As that you might have, some questions, as well as maybe some tips from past competitors. Before I continue on, does anybody have any questions on anything I've said so far, any kind of road mapping stuff, any logistics? I'll give you all just maybe a minute or so to post your answers in the chat. Give everybody about another, I don't know, 15 seconds or so. Okay, great. Then with that, we're going to actually get started with today. So today, like I said, we're going to be kind of looking at a very broad overview of the mathematical modeling process. I should mention that the figures and whatnot that we'll be using today and some of the problems that we'll be looking at during the first half are coming from this handbook, Math Modeling, Getting Started and Getting Solutions. I've put a link to the SciAm website where this handbook is is hosted on. This is a really nice resource for getting started with math modeling. And so we've taken the liberty of using some of their figures. So the idea of mathematical modeling in general is you have some real world problem based off of some phenomenon. The idea is you have some problem in fluid dynamics or defense or physics or supply chain or climate change or anything like that, right? You have some phenomenon that you have some questions about. And the question then becomes, how do I turn this real world problem into something I can quantify and maybe represent with a mathematical model? Today, we're really going to be hammering down these three components: defining our problem more precisely, making assumptions, and defining variables. All the while, we'll be thinking about researching and brainstorming. Finally, what we'll be kind of talking about in future sessions is actually building a model, getting a solution, and analyzing your model. How do you know whether a model is good? More likely than not, the very first time you do something like this, your model will not be good. So then you iterate. You come back here. Maybe you have to change your problem a little bit, make or subtract some assumptions, define some new variables, and then you keep cycling on and on and on ad nauseum until you come up with a model and some outputs that you're happy with. And then the job is to report your results to a broader audience, somebody who might not be as mathematically inclined as you are. Right? So today I'm going to be tackling this defining the problem section, and then I'm going to hand the reins over to Owen, who's going to be talking about these other two portions. All right. So what I'm going to do next is throw a bunch of text on this slide. This is going to be from a previous math modeling challenge problem. We're going to be working through this problem a little bit in order to kind of get a handle on these three components. So like I mentioned, this is the 2013 problem. At that time, this challenge was under a different name. But I'm going to get started and read off right from here. Plastics are embedded in a myriad of modern day products, from pens, cell phones, and storage containers to car parts, artificial limbs, and medical instruments. Unfortunately, there are long-term costs associated with these advances. Plastics do not biodegrade easily. There is a region of the northern Pacific Ocean, estimated to be roughly the size of Texas, where plastics collect to form an island and cause serious environmental impact. Oops, sorry. While this is an international problem, in the US, we also worry about plastics that end up in landfills and may stay there for hundreds of years. To gain some perspective on the severity of the problem, the first plastic bottle was introduced in 1975, and now, according to some sources, roughly 50 million plastic water bottles end up in US landfills every day. Plastics aren't the only problem. So many of the materials we dispose of can be recycled. Develop a mathematical model that a city can use to determine which recycling method it should adopt. You may consider, but are not limited to, providing locations where one can drop off pre-sorted recyclables, providing single-stream curbside recycling, in addition to having residents pay for each container of garbage collected. Your model should be developed independent of current recycling practices in the city and should include some information about the city of interest and some information about the recycling method. Demonstrate how your model works by applying it to each of the following cities: Fargo, North Dakota, Price, Utah, Wichita, Kansas. Okay, great. A lot of text and a lot of information as to why recycling might be really important and why this problem might be an interesting problem for mathematical modeling. Obviously, the key is what's highlighted here in yellow. Develop a mathematical model that a city can use to determine which recycling method it should adopt. So in some way, shape, or form, we're supposed to be coming up with the best recycling method, right? So this immediately comes into our first topic, which is defining our problem statement. These modeling problems in the real world are usually open-ended, so it's up to us to be a lot more precise, a lot more quantifiable about the problem we're addressing. And so this brings us to the first question I want to bring up in the chat. I mentioned this problem is asking us for the best recycling program, but how would you all define best? I'll give you all maybe a minute and a half to kind of give some ideas in the chat, and then we'll discuss them. Yep, I'm seeing lots of really good responses. Yep, I'm seeing a lot of good stuff. I'll give you maybe another 15, 30-ish seconds. Okay, I'm going to take a look at or talk a little bit about some of these responses. We got a ton of responses, and this is fantastic. I think a lot of people are talking about efficiency, but efficiency in different ways. Some people talk about cost efficiency. So how much maybe the whatever process will be the least cost to the city, right? I'm seeing a lot of most number of, let's say, plastic water bottles that we end up collecting, right? So maybe like some kind of mass or volume of plastic. Let's see. Some people are talking about understandability, trying to get people involved, right? Participation. A good recycling program that nobody is a part of is a bad recycling program. Let's see. Yep, people are talking about the city budget. People are talking about considerations. If you are a mathematical modeler that is going to pitch an idea to the city council in order to enact some kind of change, you have to take into account these kinds of more realistic things, right? A new program is going to take money out of tax, or is going to utilize tax resources, right? So these might be something important that you think about. Cheap and most effective, some kind of combination. Which method gives you the most bang for your buck, I would say, is cost effective while at the same time kind of also in a way maximizes the amount that you get, right? So the most cost efficient. Yep, I'm seeing, yeah, great. So these are all really good definitions of the word best. And I think the key takeaway is that your definition of best is probably not another team's definition of best, right? And so this is why in one case, or in one kind of perspective, it's good to have a team of people. Everybody in your team might have a different definition of best. So you can have a really good conversation as to what's going to be your best version of best, so to speak. And also, because your definition of best might be different than another team's definition of best, your responses or your solutions might be wildly different. And that's totally fine. A lot of mathematical modeling really does come down to forming an argument for for why people should listen to the math that you created, right? And another key takeaway is that this is a process that is a creative process and a process where you should be open to different ideas, right? People who are interested in cost effectiveness and people who are interested in actually gaining or getting a lot of recycled material out are right in their own regards, right? But they are different and they might lead to different solutions, right? And so this is always a really good way to get a lot of different ideas going. This is going to require a lot of brainstorming and things like that. So I've added this resource from my alma mater at UNC. This is their Writing Center website. They have a lot of really nice guides for how to brainstorm ideas, how to write reports and things like that. So now what I'm going to do is talk about this kind of brainstorming idea. What happens when you start with this question of how do you define best and then kind of keep asking questions based off of your initial definition. So this is, again, another diagram that's taken from our math modeling handbook. We start over here with the best recycling method, and they've given 3 different options. The option that processes the most recyclables, the least overall cost to the city, and most participation, which I think everybody kind of gave at least something in these kinds of realms, or maybe some kind of combination of these. If you expand out least overall cost to city, okay, well, now we have to start thinking about dollar amounts, right? So what we're going to do is think about all of these different recycling programs, and eventually we keep asking questions until we get to some kind of quantity that has to do with cost, right? So we're thinking about the operational cost of a drop-off center. How much does it cost to start up a drop-off center? How much does it cost to process? How much gas are people going to have to spend in order to drive from point A to point B to drop off the recycling, right? And this will have to deal with the size of the city, the population, all of these kinds of more quantifiable variables that we're going to need, right? So you can kind of ad nauseum, again, think about all of the different aspects of these different recycling methods you're going to need, and eventually you'll have to trim down and create some assumptions. So the first thing I'm going to do is pause for a second and make sure that I don't have any outstanding questions. Okay, great. Thank you to the volunteers for taking care of some of our questions. Now what I'm going to do is I'm going to hand it off to Owen, who is now going to talk about making assumptions and defining variables. Owen, do you want to, let's see, hopefully that, I'll stop my screen sharing, there we go.
Sweet, I will start sharing. Great, 1 second, let me get everything set up. Perfect, so as Leslie just mentioned, we just finished kind of defining the problem and talking about defining the problem, and now we need to move on to making some assumptions. So looking back at our overall modeling process, we can see that we're now moving forward in the building the model process. So what are assumptions and why do we need them? So assumptions are very important because now we have a slightly more specific problem statement, but it's still very open-ended, and we need to make it less open-ended by making assumptions. So kind of just a generic example of an assumption is a lot of times what we're trying to model is going to be related to people. So we need to think about things like, how do people interact and what behaviors do they display? So obviously each person is unique because we all have our own sets of experiences that influence how we act. But as a population, people display patterns. So some sort of assumption that you could use when thinking about a group of people is, what does the average person do? And then assume that the average person, or what the average person do, is what is going to happen in your model. So this is just kind of an example, but when possible, the most important thing to do is use data to make your assumptions, because obviously there's lots of different things that could happen, but if you can back up what you're saying is happening with data, that's going to really strengthen your model and really show the judges on a math competition or any stakeholders looking at your model that you put in time and put in research and that your model does mirror the real world. But obviously, sometimes there isn't going to be data on things, and that is completely okay. And it's often very important to make reasonable assumptions without data. So don't be worried if you can't find data for something, just try and make sure you can justify your logic for making any assumptions that you do. So be sure to justify them no matter what. And then also one more important thing is that some assumptions will arise at the beginning. So as soon as you read a problem statement, you might start thinking of assumptions, and some will arise towards the end. I know that sometimes when you're finally getting to conclusions, you'll start to realize that there are things or holes in your model that need to be patched with assumptions. So just know that you may have an initial list of assumptions, but this list will continue to adapt and change over time. And especially towards the end, when you start writing up your report, you'll probably find more and more assumptions that you need to add to your list. So now we'll do a couple of example assumptions with some questions based off the recycling problem that Keshav introduced. So we've kind of already done this first one, so we'll kind of go through it quickly. So what is meant by the best recycling method? And then one potential assumption, and remember, there's no right or wrong answer here because there's countless different ways that you can interpret this, but one potential answer would be the best recycling method will be interpreted to mean the least cost to the city. And this makes sense as one potential thing that you could consider, and then you'd want to go on and write a justification for why this assumption makes sense. Another potential brainstorming question is, what recycling methods should we consider? And if we think back to the problem statement, remember that they mentioned a couple that you could likely consider. So it'd be important to read the problem statement and see try and get some guidance from the problem statement on what they're looking for. But the example of an assumption we could use to help reduce the open-endedness of this problem would be, we consider only 4 recycling programs, one with drop-off centers, a single stream curbside, pre-sorted curbside, and a pay-as-you-throw. So you'll note this is one more type of recycling method than they had in the problem statement, but this will help us limit the number of possibilities. And now that we've seen a couple examples, I'll have you guys think of some assumptions for a problem. So this question here is, what contributes to the cost for the drop-off center method? So what are some ideas that you guys would have of potential assumptions of things we could assume that would contribute to the cost of the drop-off center methods? So if you guys want to put that in the chat, I'll give you guys a few minutes to answer that. And remember, there's no right or wrong answers here. There's countless different things that could contribute to the costs. I'll give it another 30 seconds here. Awesome. So there's lots of great answers in the chat, but it looks like some things that are common throughout them are things like staff salaries, as well as costs for property, and things like transportation costs to and from the center. Yes, also infrastructure costs and costs to run machines. These are all great answers. And remember, there's no right or wrong answers here, and the answers on the slides are just some potential things to consider. So a few things that the book says you can consider are things like the cost of the drop-off centers. So this says the cost of the drop-off center depends only on the number of drop-off centers, the quantity of recyclables that pass through each center, and the cost to operate each center. So as you guys noted, there's more things that we could consider, and we've kind of even broken down some of these even more, because cost to operate each center will include things like employee salaries and things that were mentioned in the chat. So great job with that, guys. And then we'll do one more example, and then we'll move on from assumptions. So this question is, what is the dependence on the properties of the city? And this is worded a little bit weirdly, but really what it's asking is, what sort of things do the city has to think about in terms of property? And you'll kind of note that these are nested assumptions. So if we look back at the second question and assumption, where we assume that there's only 4 recycling programs that we're considering, these assumptions expand upon that assumption and start to look at specific methods for recycling, and then make assumptions about those so that we can model them. So just note that sometimes you'll have nested assumptions like this, and that's completely normal and a good thing. But I guess back to the question. So what is the dependence on the properties of the city? The potential assumption that could go with this is that the number of drop-off centers needed depends on the area of the city, the population of the city, and the likelihood of participation in the recycling program. So that roughly makes sense, but just know there's always more factors that you can consider, but keeping it simple is also a good idea. So moving on from assumptions, we're now going to talk about the last part of that building the model section, and that is defining variables. So what variables do is kind of allow you to quantify the real world into a model. So the purpose of a model is to predict or quantify something of interest, and the variables that we use are how our model becomes quantified. So variables are going to be super important and key to your models and math in general. So there's a couple different types of variables. First, there are independent variables, and these are going to be inputs to our model. So thinking back to the recycling problem, it could be something like the size of the city may be an independent variable that will input into our model. And then they'll have dependent variables, and these are going to be the output of our model, and they're often going to depend on the input into the model. So an example of this, also back to the recycling problem, a dependent variable might be the cost of a particular recycling method, and that will depend on the size of the city and other input factors. So that's a dependent variable. And then lastly, we'll have, so my screen's frozen. Oh, too far. Let me go back, sorry. We'll have model parameters. And these are variables that are usually kept constant, and often you'll need to do some fine tuning so that they are appropriate to the real world and provide realistic outcomes of your model. So if you think about a model parameter for something like the recycling model problem, one potential parameter could be the percent of recyclable materials that actually end up in the recycling program. And that's something you can fine tune and play around with once you have your model and kind of see what a realistic value looks like using data, and then also what a realistic value to plug in to actually get a good output from your model. So those are things that you'll play around with once you have a model a little bit more, but just things to be aware of. So moving forward. So now we're going to do a little example with defining variables. So, oh, sorry, I went too far. Sorry, my computer's a little bit laggy. So to our example, so we want to create a model for the materials that we need to paint a house. So our goal here is to paint a house, and we need to think about the variables that we need inside of our model. So this is going to be a poll question for you guys. So what materials or what variables do you think should be in our model for the materials we need to paint a house? And remember, no right or wrong answers here. So feel free to put anything in the chat, and we'll take a look. I'll give you guys a few minutes to do that. Give it about another 30 seconds here. All right, so lots of great answers here. It looks like a common theme is something like we need to know the surface area of the house. We'll need to know cost of paint and other materials that we might need, or salaries for painters. Those seem to be pretty common themes, but these are all great answers. Ooh, one good question, interior or exterior. We're looking at exterior here, but interior is also a great thing that we could have been thinking about. So that's a great clarifying question. Yes. Great, so now we'll take a look at an example from the book of one potential way to model it. And remember, there's countless different ways to do this. This is just one fairly simple way to do it. And this is a lot of text, but we'll work through it. So suppose that we plan to paint a house. So that is our problem statement. So we'll need to think about dimensions of the house. So that's surface area. So that's one thing you guys mentioned. And notice they're putting units on everything here. And that's something you're gonna really wanna be sure to do is when you have a variable, be sure to define its units because it'll come in handy later. So then the next one they define is the efficiency of the paint. And this might sound weird at first, but essentially efficiency of the paint is just gonna tell you how many square feet a gallon of paint can cover. So it lets us know how many cans of paint or how many gallons of paint we will need to cover the surface area. And then note we have the units again, foot squared per gallon. Good habit to get into, just getting those units right after the variable. And then the last variable it says we need is V, or the volume of paint in gallons that we need. So these are our three variables. Remember, this is a super simple model, and there's lots of more variables that we could consider for a model, but these are just three simple ones. So now we're going to utilize the units to be able to actually construct a relationship between these three variables so that we can have a model. So if we note the efficiency is going to be given in feet squared per gallon, and we have surface area in feet squared and gallons, or volume in gallons. So we can make a relationship with that where E equals surface area divided by volume. And now we have a nice equation with our three variables. And using these three variables, we can rearrange and solve for any of the variables that we may need in our problem. So that just kind of illustrates why units are super important, especially as you get to more and more variables and more complex models, because this is obviously fairly simple with just 3. But that's kind of a quick example of how to define variables. And just note that there's always more variables you can consider, but sometimes you have to draw the line somewhere and simplify the number that you have. So now we'll just do a few more tips on defining variables. So the problem statement should determine the output of your model. Now in the last example, the problem statement was a little bit vague, but for something like the recycling problem, if we're looking for cost or something, or say in the previous problem statement, we change it to something like we want to know the number of gallons of paint, be sure that you set your model up in a way that your equations output that variable that you want to know about instead of something else. So obviously answer the question that you're asked is always important. And then next, your initial brainstorming can provide insight into which variables should be independent, which are going to be dependent, and which should be parameters. But also note, this is an iterative process, so your initial thoughts could end up being wrong, or you can realize that you need to make some changes to it as you start to make your model. And then also, like we just mentioned before, don't forget about units. Units are super important, and they also help a reader understand what your different variables are. So make sure you have units. And then finally, don't be worried if you have multiple submodels that are going to end up being incorporated into your overall model. So thinking back to the recycling problem, remember, one of the assumptions we talked about was we're only looking at 4 different recycling methods. So we could have a model for each of those recycling methods that ends up being incorporated into our overall method where each of the submodels gives the cost for a given city of that particular recycling method, and then the whole model would take the minimum cost of that, of each of the model's outputs. So don't be worried if you end up having multiple models. This is very common and can be a great feature for your model. So lastly, some homework, and just to note, homework is optional, but it is a great way to strengthen your knowledge of this material and keep your knowledge fresh for next week when we continue onwards. So the homework here is just read example 3 on page 23 of the math modeling workbook, which is in the chat. And the questions we want you to think about of this example are, what are the team's independent variables, dependent variables, and parameters? So think about that if you have a little bit of time to help keep this information fresh. So now we'll look back at the whole modeling process yet again, and we can now see that we've defined the problem, we've defined variables, and we've made assumptions. So we've done a large part of the building the model problem. So now we're going to briefly do a very high-level overview of getting a solution, and then kind of walk through some questions for a new problem statement, just to get you guys thinking about the high-level modeling process. So building solutions. This is the fun part where you get to kind of weave together everything that we've talked about so far. So once we have an initial model, you can start generating answers to your problem statement. And initially, your model may give weird or incorrect answers, and this is completely normal. I know sometimes you can end up with parameters that are adding up to too much, or you can end up getting like a negative number or something that doesn't make sense in the context of your model. And when this happens, just take a step back, look at your model, look at your parameters, and try and figure out why this happened, and then just adjust accordingly. The modeling process is iterative, so you continue cycling through until you get a product you're happy with. And then next, think about ways to represent the answers that you get. You'll want to think about including things like bar graphs, line plots, pie charts, and other creative visualizations to help people understand more about your model without having to read lots of text. And I should also note that things like line plots and bar graphs and things that are tracking your model over time can be very helpful in figuring out where your model is going wrong or where something weird is happening if you are having some issues with your model. So also be sure to include those when you're working on your model, because they can help you quickly get to answers about strange things happening in your model if there is something weird going on. And then lastly, an important question is, can you simplify your model if it is complicated? A lot of times people gravitate towards really complicated models initially because they think they might be better or might win more points with the judge or something, but that is not always the case. Sometimes it's better to have a simpler model because there's going to be less cases or less places to introduce uncertainties. And also it's going to be easier to understand what your model is actually doing and understand the behavior of your model. So take a step back, look at your model, and see if you can simplify it. Is another great thing to do while you're building a solution. So just to reiterate, this is the step where you synthesize your assumptions, variables, and models into one coherent piece that weaves together everything you've worked on so far. And this is my favorite part of this modeling process because you get to bring everything together and start working towards answering your question. So now we'll do kind of a brief overview problem where we'll have you guys answer some questions. But first, I'll look at this problem statement on the left. And this problem statement is very brief, and we'll go through here. So we all dread getting sick. Years ago, illness didn't spread very quickly because travel was difficult and expensive. Now thousands of people travel via trains and planes across the globe for work and vacation every day. Illnesses that were once confined to small regions of the world can now spread quickly as a result of one of the infected individuals who travels internationally. And now we'll get to the actual question. That was just some background. So the National Institute of Health and the Center for Disease Control and Prevention are interested in knowing how significant the outbreak of illness will be in the coming year in the US. So just initially taking a step back and looking at this problem is super open-ended and there's not a whole bunch of information off the bat. So we'll kind of work through our modeling process here. So this will be a poll question for the chat. So put your answers in the chat. What questions do you have or what information would you like to know about this problem? And remember, we're just trying to get a better feel for the problem at the moment and get some more specific answers. So feel free to put your answers in the chat and I'll give you guys a bit of time to do that, a minute or two. So I'll give another 30, 45 seconds here. All right, so there's lots of great answers in the chat. Some common themes are things like, what data do we get is a great question. That's not clear from this problem right away. Also things like, how fast does it spread? What type of disease is it? How many initially affected people are there? Things like death rate and what is considered a significant outbreak. These are all great questions and things that you need to think about or are great things to start thinking about initially. So I guess this is very open-ended and obviously we're not actually doing this problem, so we don't have any data, but things like getting that data right away and starting to think about it is great. So those are some great thoughts. So the next question we would think about is kind of what precise problem would you want to tackle? So how would we narrow down to a more specific problem? So I guess since we don't have the full problems here, we'll talk about what you would probably be given would be some data on the illness that you could use to start to construct a model. So using that data, you could kind of narrow down the problem. And I guess some things to note in terms of the scale of the problem, we can see in the problem statement that it asks in the coming year. So we know that we can limit our time scale to just the next year. So that also helps narrow our problem down a significant amount. So then I'll have you guys do the assumption problem next. So in the chat, what assumptions would you like to make to tackle this problem? So remember, we're dealing with some sort of disease in the US, and we're only modeling for a year. So what are some assumptions that you guys would like to make? And I will note, I'll read Wesley's comment aloud here about when the problem was published. So it was published in 2014. So that was before COVID was on the author's minds, but it is definitely a very relevant problem right now. Give it another 45 seconds to a minute here. Give it another 15 seconds, and then we'll talk about some assumptions. All right, so a couple common themes that I've seen throughout all the different great assumptions that have been put in the chat is things like assume the number of people affected is constant. And that is a fairly reasonable assumption potentially in this case, depending on the death rate of the disease, because we're only looking at a year. So the birth rate shouldn't be too significant in the US. So that's a good assumption to help simplify it. We also have things like assume that disease spread is uniform. That is a good assumption because if you start to think too much about population dense areas versus unpopulation dense areas, you could potentially end up with a very complicated model, especially considering the time frame of the problem isn't significantly long, or time frame of the competition is only 14 hours. Another good one is assume that an infected person is only contagious once they have they have a positive test for the disease, so there's no like pre-contagion phase before they've been identified. But yeah, those are great ideas, guys. So those are some potential assumptions, and then just remember you want to justify those assumptions when you do write up a solution. And then the last question we have here is what variables might you introduce? And we'll just briefly go over a couple different variables that you could introduce. So you might want to think about things like the number of susceptible people in the population. And note this will change as your model goes on, as more people get infected. You also want something like the total number of people in the population. Or you might want something like the rate of spread of disease or the rate of transmission of the disease. So if someone comes into contact with an individual who is infected, what is the probability that they will also become infected? And that could be a parameter of your model that you'll have to fine tune with data. So those are just a couple examples, and kind of, hopefully this was a helpful example to kind of walk you through all the steps kind of together on an example. But this will lead us to our next homework piece. So this will also be kind of related to a disease spread model. So some homework, again, the homework is optional, but it's great if you do it because it will help keep this information fresh in your mind and give you some extra experience with this subject matter. So look at example 2 and 3 on pages 27 through 30 about the disease spread models. And then think about these questions. Think about how do they represent the results of their model, and what are the dependent and independent variables? What are their parameters, and how is the constant rate disease model modified, and how do the results change with this modification? So that is some additional homework if you want to look at that this week. So now we'll talk about a couple of things that we'll just briefly touch on, but we'll go into way more depth on in later sessions. So now we'll talk about analysis and model assessment. So the motivating question here is kind of how stable is our model as we vary parameters? So if we think about changing a parameter just a little bit, how much does that affect the output of our model? And this is important because doing this analysis and model assessment will help you think about the strengths and weaknesses of your model and let you understand better how sensitive your model is to different inputs. So this is a super important section, and we'll go into way more depth about this later, so don't worry if you're confused about it now. And then lastly, we'll talk about reporting the results, and we'll have a whole section on this as well later, but the motivating question behind you want to be thinking about when you are writing up a report is, how do we convince others that they should use our model? Because obviously, if we have a great model, but we can't convince anybody to use it, it's not going to be useful. So we want to think about who are we communicating our model to? So for example, like the M3, you want to think about communicating it to highly mathematical judges who have a lot of knowledge of math and want to know all the specifics and ins and out of your model. But if you're trying to communicate something to the general public, you'll want to think more broadly, think about having really nice graphics or short sentences and things that are easy to understand instead of going into all the nitty-gritty of your model. But again, we'll have way more information on this in a later session. So that pretty much brings us to the end of the session, but there is a little bit more homework here at the end. I think this problem is really fun to think about. So the last bit of homework is think about a problem you might encounter in your life and then start to think about how you would model it. So obviously we encounter countless different problems in our lives that we can potentially apply math to. And then we'll give 2 examples here just to kind of get your juices flowing and start to think about problems in your own lives. So the first example is, if a gas station is further away but has cheaper gas, should you go there or use a closer gas station, assuming that you're driving to the gas stations, of course. Then lastly, if you're going grocery shopping, what is the quickest way to get everything you need? So this will be a fun thing to think about and kind of look for in your daily lives, different things that you could try and model. But that is the end of this presentation. I think we have a few minutes before we're planning to start the practice problem session. So I guess we can take a few minutes break and reconvene on the hour. But thank you guys.
Okay, welcome back, everybody. So for the second hour, we're going to be diving really deep into the 2019 MathWorks Math Modeling Challenge problem. We're going to be looking at the problem itself, the data sets that are provided with the problem, and then we're going to go in and think about what we've talked about today in terms of defining a problem, making assumptions, and defining variables, and then I'll kind of brush over some ideas for how to actually tackle problems. All of these questions, or the usual format for the M3 challenge, is a 3-part question, or three parts to the problem. We will likely only be able to get through the first one in depth and then maybe talk a little bit about part 2. And as we continue on with later sessions, we might be able to go a little bit faster. But I want to make sure that we spend a good amount of time thinking about this problem here so that we get our feet, or so that we have a good understanding. All right, so we're going to start with the 2019 problem. As I've said, the problem is given here at this link and the data set is here. And so I'm going to immediately move over and I'm going to put this in the chat so that everybody can have access to these links. And I will go to this said link. So this problem is titled, "One is too many and 1,000 not enough, substance use and abuse." So this is a HTML version of this problem statement. In the actual challenge, when you go to download the problem, you'll actually be given a document that looks something like this. And so we'll just read off from this document. So I'm going to just get started from here and go through all this, this introduction stuff and then read part number 1. Substances such as tobacco, alcohol, and narcotics can affect the physical and mental health of users. The consequences of substance abuse, both financial, healthcare, the criminal justice system, workplace productivity, etc., and non-financial, divorce, domestic abuse, etc., ripple through society and affect more than just the user. The effects of substance abuse on individuals and society have come to the forefront recently as opioid addiction has become prominent. Efforts such as taxes and regulations on cigarettes and the drug abuse resistance education program have been made at the local, state, and national level to educate, control, and/or restrict the consumption of such substances. Such efforts need to start with an understanding of how substance abuse spreads and affects some individuals more than others. Part 1, it's called Darth Vapor. Often containing high doses of nicotine, vaping, or inhalation of an aerosol created by vaporizing a liquid is hooking a new generation that might have otherwise not have chosen to use tobacco products. Build a mathematical model that predicts the spread of nicotine use due to vaping over the next 10 years. Analyze how the growth of this new form of nicotine use compares to that of cigarettes. All right. So again, these last 2 sentences are really the key pieces here, although there's some interesting information in general in this problem statement. So we're going to build a mathematical model that predicts the spread of nicotine use due to vaping over the next 10 years and analyze the growth of this new form of nicotine use and how it compares to cigarettes, all right? And if you keep scrolling down in this document, what you'll see is some extra information. There are obviously three parts to this problem. Some important information as to how your solution should look. You should submit a one-page executive summary, and your solution paper, with a maximum of 20 pages. And you can also choose to include code and whatnot. So there's another page that gives a data set or a couple of different data sets. And what I'm going to do right now is actually take a look at this data set and this third figure provided. All right, if you click on this link right here, you're going to be brought to this page right here where you can click on all of these data sets. These will download some Excel data sheets, and this will give you a PDF. So the first thing I'm going to do is move over here. This is the first link, and the information in here is percentage of high school students who used e-cigarettes in the past 30 days by gender and race or ethnicity, National Youth Tobacco Survey between the years of 2011 and 2015, right? So over the course of 5 years, we have some information as to the overall percentage of people who choose to use e-cigarettes in the past 30 days, right? So if you take a look, for example, right here, this is information on the overall number of e-cigarette users in each of these years, and they also give 95% confidence intervals, and they also give standard errors. And then they break down by gender or race and ethnicity, right? So this is potentially useful information for this problem. The next thing I want to do is look at this figure, which gives a historical context for cigarette consumption. So it's this one right here. So they've also provided a one-page summary of the per capita number of cigarettes smoked per year. So this is now a number of cigarettes smoked per year over, it looks like, over a decade, or over a century, right? And then there are some nice kind of points here that talk about major historical events. Obviously, a lot has happened in this century, right? And this just gives a little bit of information as to where this data set comes from, okay? So what we're going to do during this problem solving session and what we'll be doing in future sessions is we're going to be coming back to our diagram for how to tackle how to tackle real world problems in the language of mathematics. So what we're going to do today is think really hard about these three sections: defining the problem, making assumptions, and defining variables. All right. We won't have a whole lot of ability to research and brainstorm. I'm not going to do that in front of you all, but we'll be thinking about, just with the information we have available to us, how to think about these three things. So to begin, let's think about an initial problem definition. If you all could, in the chat, come up with a more precise or more quantifiable mathematical statement for our problem. And this may have been the smart thing to do, is to put this question in the chat. So again, this was the problem in the chat. I've put the question that was asked in the competition. And now I'd like you all to think about some more quantifiable ways of defining this problem. I'll give you all about a minute and a half. Yep. All right. I'm starting to see some good stuff. I'll give everybody another maybe 30 seconds. Okay. I'm seeing some good stuff here. So some responses that I'm seeing are, for example, percentage of the population that is vaping in a given year over the next 10 years, right? Let's see, the rise of nicotine use due to vaping, right? So when we think about the rise in nicotine use, there might be a couple of different ways of thinking about that. We might be thinking about the number of vape pods that are sold or used per year. We might think about the overall amount of nicotine that is contained in these cartridges. Let's see. Some people are thinking about the number of people who are starting to vape as opposed to just the total number of people, or the current total number of people. Some people are thinking a little bit about some graph theory stuff, thinking about how nicotine use kind of spreads in a population, I think is what the kind of idea I'm getting from there. And that might be actually more relevant in part 2 of the problem. We'll be getting to that maybe towards the end of our session. Let's see. And of course, plenty of people are talking about comparing the spread of vaping and cigarettes, right? So we're thinking about how does it increase, how does it decrease, and what time scales, things like that. These are all really good. Let's see. Yeah, I think I've covered most of these. Yep. So something I might just point out is that we need to make sure that when we say, when we talk about finding trends or projecting spread or something like that, we need to make sure that we have a quantifiable metric that we are finding a trend for, right? So when we're looking for the trend we have to be looking for the trend in number of people or the trend in the percentage of people or something like that. So I'm just going to give some ideas in the chat, of course, or sorry, I'm going to give some of my answers here. Of course, the things that are in the chat are great. And of course, no two answers are going to be exactly the same, or there's no one right answer. So some ideas I came up with: what is the expected number or percentage of teens who vape over the next 10 years? And as I was reading the problem, I realized that even though the first half of the question talked about teen vaping, the actual problem question did not talk about teens at all. So you could choose to talk about teens or you could choose to not. That is, I think, something that you might be have a little bit of leeway in terms of what problem you're going to be thinking about. Another question that I kind of like doing whenever I'm working on modeling questions is, what is the minimum expected number of percentage of teens who vape over the next 10 years? This might be useful for a more public health perspective, and it might be a little bit easier to model, because if you can think about something like, if your minimum expected number or expected percentage of teens who vape is, let's say, 50%, well, that's really bad, right? So thinking about minimum and maximum expected number or percentage of people who vape might be an interesting thing to think about and might help you simplify some of the work that you have to do later on, right? Because if in the worst case scenario, there are a lot of people, or sorry, in the best case scenario, if there are a lot of people who vape, that already tells you that there's going to be a problem down the line, right? We might not need to care about the expectation of number of people who vape. Let me make sure I'm looking there. Okay, great. Yeah, so great job on that. I think a lot of people kind of came to the conclusion of around number of people or amount of nicotine used in the next 10 years. And of course, compare that to the rise of cigarette use. Okay. The next thing we're going to do, oh, excuse me, right, there was another option here. What's the expected number of vape pods used? Again, the goal is to reformulate the problem to ask something quantifiable. We need to have some kind of number, right? If people are thinking about, x-axis versus y-axis, we need to have something on the y-axis that we can actually create trend lines for or do some other kind of mathematical modeling for. And units are important as well. Okay, so we've thought about our problem. We have some idea of what kinds of problems we're actually going to tackle given the initial problem statement. Now, what kinds of assumptions are we going to need? I'm going to give you all a couple minutes to give some ideas in the chat. This one might be a little bit more nebulous, but the idea is to come up with some simplifying assumptions that we might need in order to tackle some kind of problem that's as big as, vaping across the entire United States. Okay, good stuff so far. I'm going to give everybody another, say, 30-ish seconds. Okay, so let me go through some of these assumptions. There's a lot of good stuff, some stuff that I didn't even think about. Let's see. So some assumptions are based on the population. So you were assuming that the populations are going to follow some kind of known trend or continue on with the same trends that we've been seeing over the course of 10 years. One assumption you could make is that the population is constant, right? That is an assumption that you would just have to justify for yourself. Let's see, there's some assumptions are if a vape pod is bought, it will be used. That's a good one. Obviously, that's not always going to be 100% the case, but certainly if we're going to be using sale data in order to come up with our solution, we have to make that assumption. Let's see. Somebody had another one that was good. Users use until the end of their life. So basically, you're assuming that nobody quits using cigarette or vape pods. That would be like a worst case scenario kind of situation. Let's see, there was another one I saw and then I lost it. Let's see. Oh, somebody said if a person vapes once, they're considered a vapor, just in general for life. Or for the purposes of this model, at least. So that would kind of be similar to actually the one that I talked about before, users use until the end of their life, right? So that is something that you can define. The data set that I had shown you was people who had vaped in the last 30 days. So you might also make that assumption instead, right? that if you vaped in the last 30 days, you are a vapor. Some people talked about policy changes. That's a good one. Or the fact that these e-cigarette companies aren't just stationary, that they will probably be coming out with new products to try and entice more people. So you might assume that that will not happen, because otherwise you can't really predict what the marketing tactics are going to be 10 years from now. That would be fairly difficult to do. Let's see, anything else? Yeah, so some people are thinking about kind of birth-death processes and thinking about is the death rate different if you're vaping versus not vaping. I think this is good. This is a lot of good stuff. Again, some of these things I didn't even think about. I'm going to just kind of flash a whole bunch of assumptions that I thought about. Again, I assumed that a teen, and I was thinking about teens when I thought about this, when I read the problem earlier, but I would assume that a teen is between an 8th or 12th grader, because this roughly corresponds to 13 to 18-year-olds, which is exactly what I would define to be a teen. I assumed that the total number of teens is a constant and evenly divided among the 5 grades, right? I just assumed that the year-over-year change in students is likely pretty small, and that we can ignore the fluctuations in student populations, right? This is something that I would argue as something that I would want in my model. Obviously, I think that if you took into account population trends, you could easily not make this assumption. I assumed that vaping refers only to nicotine-based vaping, right? There are other types of vaping out there. And for the second part of the problem, when we're comparing to cigarette use, I think it's best to compare apples to apples. And then I also assumed this, which might come in handy later. Assume that influence by a current vapor is the only way non-vapors decide to start vaping. And I would actually have to come up with some kind of citation to back up this claim that I've just made here. But I am assuming that peer pressure is known to be a major driver, and the fraction of people who vape based 100% on their own desire is likely pretty small. They've likely heard about vaping or seen other people vape and then thought, yeah, maybe I should try that, right? Again, there are tons of assumptions that you can make. Assumptions might be based off of a model that you've already developed, right? People who are familiar with SIR models might understand why I could have come up with this kind of assumption right here. If you don't know anything about SIR models, don't worry, that will come up in future workshop sessions, right? But the things that came up in the chat were fantastic. This is great. Thank you so much, everybody, for your participation. Okay. One final note that I will make is that when I wrote all of my assumptions, I also gave a justification. This is something that Owen had mentioned in the first hour. Justifying your assumptions is always something that will be really helpful for judges to look at your work, and also for mathematical modeling in general. If you justify your assumptions, it's easier to have a dialogue with other professionals, right? So if you can explain why you've made a choice, or if you're reading somebody else's work and you think, why did they make that assumption? And they explicitly give you a justification, that allows you to understand their work a little bit better, and dialogue can happen a lot faster, right? So this is really advice for the future as well as for this competition, all right? The last thing is, the last part of our little wheel is variables and parameters. So again, I'm gonna give you all about, I don't know, a minute and a half or so, and give me some ideas for variables, parameters, inputs, outputs we might want from a model that is trying to answer this question. Yep. I'm getting a lot of really good stuff here. I'll give everybody another 30 seconds or so. Okay, great. There's some things here that so obvious that I didn't even think about, right? One obvious variable or parameter is time. I didn't even think about that one. That's a good one. Number or percent of new vapors. This is obviously, or could be, I mean, it's not obvious at all, that it could be related to the output or the problem statement that we have defined, right? The price of e-cigarettes or vape pods or anything like that, right? Cost could be something very important. Let's see, population obviously is something important. And again, based off of your assumption, that might be a parameter that is constant, or that might be a variable that changes over time, right? Let's see, the total number of teens. One person really thought hard about how high schoolers use vapes in terms of number of bathroom stalls per high school. That was a good one. The rate of influence, how likely is it that somebody influences another person to use e-cigarettes? The addictiveness of nicotine itself could be very interesting. Let's see. Yep, dollars spent on advertising. Somebody else talked about campaigns against vaping, if that's something that you want to think about, these kind of larger public health changes against vaping. This is a really good one. And I might touch on this a little bit later when I'm trying to give you all some tips later on. Okay, yeah, these are all really great. Some of the parameters that I thought about were percentage of teen vapors in the last 5 years. Let's say that I wanted to use past data. Some people might be only interested in the current number at this time and then use that as initial conditions. The total number of teens, the number of vape pods used, this kind of influence rate, the population rate increased. And as I kind of mentioned when I was looking at your chat responses, based on your assumptions, you may or may not need these variables. Some of these variables might be parameters that are pretty much constant throughout your model, right? These are other considerations that you'll make. And this is why kind of the problem statement or the problem definition that we made, our assumptions and our variables all kind of talk to each other, right? They're all kind of different components that when you define or when you hammer down one of them, you might need to change something else, right? Okay, great. This is awesome, you all. Thank you so much again. Okay, very important. Your problem statement or your version of the problem statement, any assumptions you make, and your variables should be explicitly stated in your write-up, right? A problem statement, a lot of times what teams will do is they'll say, here's our version of the problem statement or problem statement reformulation or something like that. Assumptions are often like given as a list. Variables can be given in some kind of table, right? And you should always cite where you get your information from, things like that, right? But these should all be explicitly stated in your write-up, right? And this is very important if you want judges to really take note of your work. Okay. So we have the kind of structure of what kind of question we might be interested in, the kind of assumptions that we're going to make, and some of the input, output, and model parameters. Now comes the fun part where we think about what kind of model we should build, We can think about statistical models. We can think about difference or differential equations in terms of SIR models. We can think of a probabilistic model, or we can think of some kind of agent-based model, or potentially even like some kind of graph theory kind of problem. We're going to be thinking about 2 and 3 later on in other workshops. And today I'm going to be giving you some ideas for how to tackle this problem using options 1 and 2. Again, if you aren't super comfortable with SIR models or SI models or anything like that, don't worry. We'll be talking about that in future workshop future workshop sessions. Okay. The very first thing I want to do is just give you some tips on what kind of model to pick, right? Obviously, one thing should be comfort in using a certain framework. Like I said about SIR models, if you're not comfortable using SIR models, don't use them. It'll be pretty obvious that you don't know what you're doing, and that'll look pretty poorly on by judges. I think Owen actually mentioned something in the first hour, which is that you shouldn't go too above and beyond. Sometimes simple is the best way to do things. Consider the amount of time that you are allotting yourself. So in the M3 challenge, you're only given 14 hours. It's not a great use of your time to spend 7 of those hours on the very first problem, right? So you want to make sure that you leave ample time for the more difficult problems. Problems 2 and 3, as you'll see in a little bit, are much more difficult. So you want to just kind of make sure that you can answer problem number 1 well, but basically just answer it and then move on, right? Another thing, consider the number of assumptions that you need. This is something that might be kind of relevant, maybe more towards like maybe outside of the M3 challenge. But if you give a paper and you have 50 assumptions in your model, and you say if 50 different conditions are met, then my model is fantastic. Well, that model seems like it's very narrow in scope, right? Sometimes simplicity in terms of number of assumptions, in terms of mathematical framework, is really nice in terms of being able to predict the real world, which is much messier than most mathematical models can accurately predict, right? So these are just kind of my 2 cents on what kinds of models to pick when you're coming up on the M3 challenge, right? So now I'm going to give you some ideas for how some people have and how I might think about tackling these problems. The first method would be some kind of statistical model. I have some data on past use of e-cigarettes, and then I try to fit some kind of curve to this data set, right? Obviously, one of the simplest things you could do in all time is to just do a linear fit, right? There are obviously ways in which you can tell whether a linear fit or any kind of fit is good or bad. And this way, well, this is not incorrect, right? In terms of just predicting a rise in e-cigarette use. Another kind of fit you could do, this was actually taken from a submission that I was reading on this problem, is apply a Gaussian fit. And they argued why a Gaussian fit makes the most amount of sense, because they came over here to wherever, I'm sorry, I'm having trouble finding it. Here we go. They came over here to this data set on cigarette use, and they said, well, this looks pretty Gaussian. So maybe vape use or e-cigarette use will also follow this kind of cigarette use as a Gaussian curve. I thought that was a pretty good idea. And so I've just recreated their fit. I've recreated the fit on this plot right here, right? So this could be a statistical model. A big advantage of a statistical model is that it doesn't use a lot of assumptions, right? You don't have to assume a whole lot about how things are changing over time, how different policies are enacted, or different changes to how addictive the chemical is over time, or anything like that. You're just using past data to predict future data, which could be very useful. The other kind of model you could generate is an SIR model, or some kind of model for disease or information spread over time. These are using differential equations, which again, we're gonna talk about in future sessions. If you are aware of what SI models are, I've chosen the absolute simplest SI model available right now. People who are susceptible to vape use can become infected or become vapors over time. And I've plotted this over time, right? And so then one question becomes, what is this parameter A? You either have to come up with it by using some kind of regression tool again, or you have to find some information about this parameter A in the literature, right? So this obviously complicates the kind of problems that you can do, but you get more interesting behaviors in your outputs, right? This is clearly not linear, and this is definitely, well, if you know anything about SI models, this is going to be logistic growth, which is certainly a much more interesting behavior than anything you could maybe get from just a simple linear regression, right? Okay, great. Does anybody have any questions about anything we've talked about in terms of this first problem? Again, I'll give you all maybe 30 seconds or maybe an hour. Oh, not an hour, a minute. Okay, a couple questions. How much data will we be given and how much research will we have to do for the competition? This is completely up to you. Technically, you don't have to use any research and you don't even have to use any of the data provided to you by the competition. This is completely up to how you choose to handle the problem. And I know that's not a very good answer to this question. Usually your data sets won't be extremely large. You won't have terabytes of data available to you. Again, I kind of showed you this data set, and this is fairly sparse, I would say, in terms of, considering that certain companies are using petabytes of data in order to do their statistical algorithms, right? So they won't be super computationally intensive, let's say. But again, you could choose to add more of your own data using your own external research. Again, for the competition, I would urge you to consider the amount of time that would take to find information that you might not have readily available to you. What kinds of resources are we allowed to access? Are we allowed to look up data during the competition? Again, the entire internet is available to you as long as you should cite your sources, obviously. And you should be able to do any kind of research that you need in order to gain extra data. Are we only allowed to use the information given in the problem statement? No, not at all. In fact, actually, if you take a look at this data set that was provided by the M3 challenge, they actually give you the source where they collected this information. And this is actually a really long report about all of this kind of stuff. E-cigarette use among youth and young adults. This is obviously something that could be easily looked at in terms of, you have this available to you, and you could take a look at this really, really big document in terms of all of the possible data that's available to you. So you could do that as well. Okay. Somebody else asked if we could implement both statistical and SI models. Okay. One of our volunteers is handling that question, so I'll let them do that. Great. Okay, then if there are no other questions, I'm going to continue on, and I'm going to talk about next steps. So we built some kind of model. Maybe you like the SI model, maybe you like the statistical model, maybe you think that neither of these are good models or models that you should use. But then the question is, how do we know that we have a good model, right? Some ways that we can show this are using data to compare to, right? We could calculate some kind of R² value in terms of how good our regression is. We could do some kind of sensitivity analysis, which again, we'll talk about in future sessions. But the idea is if you change one of your input parameters by, let's say 10%, could be any number, how much does your result change? So in the real world, if there's a little bit of noise, how much would that change our actual result if you used our model, right? These might be interesting questions to ask in order to show how good your model is. Okay. Obviously, the last part of this problem is to compare to the rise in cigarette use. So the problem or the solution that I had shown you from one of the past competitors, they obviously compared to that data set on cigarette use and just kind of compared Gaussian curves. So they'll say something along the lines of, well, both of them seem like Gaussians because of how our assumptions are, right? I'm not going to go into kind of details on here. I think it's more prudent if we continue on with problem number 2. So what I'm going to do now is back out of the slideshow again and come over here to our PDF. And now I'm going to read problem statement number 2, which is titled Above or Under the Influence. Like nicotine, the abuse of most substances is correlated with numerous internal and external factors that affect the likelihood of an individual becoming addicted. Create a model that simulates the likelihood that a given individual will use a given substance. Take into account social influence and characteristic traits. For example, social circles, genetics, health issues, income level, and/or any other relevant factors, as well as characteristics of the drug itself. Demonstrate how your model works by predicting how many students among a class of 300 high school seniors will, with varying characteristics, will use the following substances: nicotine, marijuana, alcohol, and unprescribed opioids. Again, there was a lot more meat to this problem, but again, I'm just going to highlight this part. Create a model that simulates the likelihood that a given individual will use a given substance. Extremely vague, right? These problems certainly get a lot more difficult as you go on. So now I'm going to come back. I'm going to paste this here in the chat so that everybody can see what I've highlighted here. And now I'm going to come back over to our slideshow. Okay. And again, I'm going to ask you all to think about a problem definition. How can we more quantifiably write down this problem statement that I've put in the chat? So once again, I'm going to give everybody about 1.5 minutes or 2 minutes to think about this. Yep, good stuff so far. Give everybody another 30-ish seconds. Okay, great. Some good stuff here. Let me read some of this out. Plenty of people have given me some kind of indication of a probability. What is the probability that a given individual will buy some kind of or use some kind of substance or product? One option that I kind of like is make a scoring guide on an individual's likelihood to use a substance. So in my mind, what this sounds like is instead of giving a probability, you're giving some kind of risk assessment. You're doing something like low, medium, high risk, right? Let's see, what's the percentage of a given population that uses each substance? And again, thinking about how other factors can influence this probability, like conditioning on other drugs, age, gender, things like that. One person said, if you think about the percentage of your neighbors that start vaping as some kind of input to your model, what is the probability that you or a given person will start vaping, right? And I guess I should say that since the problem statement asks specifically about multiple different types of substances, you would generalize to those different types of substances. But again, this is pretty good. Again, I think that we're starting to get to a place where there's a lot more variability in what this problem definition means to people. So some of the problems that I thought about, or some of the definitions I thought about, were determine the probability that an individual will use a certain drug, and calculate a risk metric for an individual's chances of using a certain drug, right? So the idea is you have some individual, either it's a probability 0 to 100%, or it's some risk metric. It's just some kind of statement, low, medium, or high risk, or anything in between, right? Okay. The next thing is variables and parameters. I wanted to jump to variables and parameters before doing the assumptions, but now let me ask you all to think about what information we're going to need in order to tackle a problem like this. Again, I'll give you all about a minute and a half. All right, another 30 seconds. There is a ton of stuff here. Okay, great. Yeah, there's a ton of stuff here. Let's see. So location is, I think, something that's important, right? Certainly in the US with the opioid pandemic, there are certain regions of the United States where the problem is much bigger than others. I think one interesting thing is the probability that individuals will also use other substances. So the idea of maybe like a gateway drug, right? If you're using one substance, you might be more likely to use another substance. Things like race, socioeconomic status, mental health, your distance away. If you're thinking about a graph network, your distance away from somebody who's using a certain substance. Let's see, average income. Obviously, you would need things like population. Let's see, am I missing something? Other kind of risk factors like gambling, that's good. I'm seeing some stuff about genetics, which is good. in my opinion, it's kind of hard to think about genetics as a quantifiable variable. One person just said, like, what do they say? Something like a genetic predisposition also on a scale, or on some kind of scale. So you would use some kind of just non-dimensional parameter, like, your genetic predisposition is 100%, something like that. You would have to kind of explain what that means, or maybe there's some external data out there that kind of gives you this information. Yep, a lot of really good stuff here. Awesome. Okay, so I'm gonna show you what kinds of things I thought of. Some are provided by the problem statement, right? Things like income level or presence of other health issues. Some things that I thought of were the aspects of each substance, right? How much does it cost? Is it a legal substance? In some places, marijuana is legal. Some places it's not. Does that change how likely somebody is to use that substance? How addictive that substance is? Maybe the potential for overdosing, right? This could factor into like birth, death kind of things. The output of our model, I would say, is either some kind of probability or some kind of risk level for each of these substance uses, right? As I was kind of thinking about these variables and parameters, I quickly realized that I myself don't know enough about drug use and things like that to think about a lot of these different parameters. So this tip for just beyond the M3 challenge, and obviously at some point this is relevant for the challenge itself, is that collaborating with non-mathematicians is really helpful to be able to understand what things are already quantified by a certain community, what kinds of data are already available, things like that, right? And again, this kind of ties back to what I said at the very beginning of the session today, that getting together with a lot of different minds of different backgrounds will really help you think about how to best come up with a mathematical model. Because things like this are not cut and dry, they're not black and white, they're not things that a mathematician, once they're given all of this information, they might be able to use this information to build a nice model, but all of this initial stuff is something that's a lot more of a creative process, right? The last thing that we're going to be doing today is thinking about assumptions. So let me see if you all have any ideas for what assumptions we might need in order to tackle some problem like this. Again, I'm going to give you all about, I'll give you all about 2 minutes for this one. All right. Give you all another maybe 15 seconds or so. Yeah, there's some good stuff here. I would say that this this part, making assumptions, is going to be kind of difficult without maybe starting to build some models and maybe kind of playing around and seeing, oh, I might need this assumption in order to finish making this model or something like that. So you all given me some pretty good ideas. Let's see. So I'm seeing plenty of like network theory kinds of responses here. So some ideas of connectivity of a community, things about pricing and cost, assuming that a cost is constant or that it increases just based off of inflation. The addictiveness of certain drugs. Some drugs are more addictive than others. Things about prior risk. Let's see. Thinking about recovery as well. That might be something worth noting. Yeah, again, pretty good stuff. Okay. So again, I'm going to just kind of flash a whole bunch of assumptions I thought about. One thing that I think is a good assumption to make in these kinds of situations is to assume only the factors of race, ethnicity, gender, and socioeconomic status influence substance use. Why is that? Well, simply because there are far too many factors to take into account, right? In order to tell the judges, these are the things that I'm going to be thinking about. These are the only ones. Maybe you have some information as to, oh yeah, these, according to some study, these are the main drivers. That might be something that is relevant for the competition. I thought to assume that the use of one substance does not influence the use of another. I saw somebody, maybe it was a previous question I asked, that actually thought about the opposite thing. They did want to assume that substances influence each other's use. And my argument is simply, this is a simplifying assumption. Again, in the context of the M3 challenge, it's totally fine to say I didn't have enough time or just there is a lack of data on stuff like this. So we're just not going to assume that for now. Maybe in the end of your section, when you're thinking about limitations or future iterations of your model, this is something that you would say, I would love to relax this assumption, right? I also assumed that addicted, the definition refers to substance use in general, because it's really hard without some kind of trained professional telling me that somebody is addicted to a certain substance, whether or not somebody's actually addicted, right? And if you were to ask people in a survey, are you addicted to nicotine, they might not be willing to say that, right? So you might not be able to get accurate information from people through a survey. But use would be something that's much more easily or much more black and white, something that people are more likely to admit to, especially in an anonymous survey, right? Again, assumptions that you all have given me are great. And I know we are pretty much out of time, and that pretty much concludes the amount of stuff that I had for you all today. Just as, again, homework, quote unquote, practice using this kind of modeling setup process on other past M3 problems. We're going to be doing this for some of the most recent M3 problems. But if you are interested in doing this yourself on your own, and then maybe coming back once we're actually doing those questions, you might have a little bit of a leg up. Obviously, do this with your team if it's at all possible. This is going to be a good way to practice with your team and understand how other people think. This might be just really good idea for how to proceed with the competition itself. Again, the steps would be to define your problem, make and justify assumptions, define variables and parameters, right? And then if you're feeling confident, you can start building up models. But again, we're going to be thinking about these things in future workshop sessions. Very important. This is super important for the competition itself, and certainly just in life in general. Write down your progress as you go along, right? You only have 14 hours for this competition. If you wait to do all your writing at the very last minute, you're not going to have a nice product for judges to read, right? So you should always write down your progress as you're going along, right? With that, I believe we are pretty much done. Let's see. There are a couple lingering questions. Let's see, anything else? Nope. If there are any burning questions, again, feel free to reach out to us via our email. It is hsmathmodeling@math.utah.edu. You can always reach out to us via email. And again, this information will be available afterwards. You will be able to see all of the slides that we used today on our Google Drive. In the future iterations, when we're actually working with code, you'll be able to see those in the future. And again, the handbook that I used, or that Owen and I used for our figures and things like that, can be found on both the SciAm website and the M3 Challenge websites. With that, unless anybody else from our volunteers, leaders, or anybody from SciAm, unless anybody else had any last minute things to add, I believe we are done. All right. Thank you, everybody, for attending, and thank you so much for the participation. This was great.